So I should start now.
Yeah, we are ready. It's a great pleasure to welcome Rajeev to our seminar, our virtual seminar, and thanks for agreeing to tell us about Helicity and quantum group in classical hydrodynamics.
Thank you. Yeah. Thank you. Yeah, it's a great pleasure to be here and to see so many familiar faces, even some people I haven't seen in a long time. So this is great. Yeah, so I want to talk about an old problem in theoretical physics, perhaps the oldest unsolved problem, and that is to understand classical incompressible hydrodynamics. So I mean, in true American fashion, I should begin with an advertisement, with an ad. So the review of fluid mechanics I'll give is basically taken from a book I wrote recently. I've always had a deep appreciation for fluid mechanics, and late in my career, I'm returning to it, and hopefully with a little bit better understanding of the math than I had when I first learned it many, many years ago. So let me start by reviewing a few basic facts about fluid mechanics. I assume much of this is known, but I just wanted to set the sort of the background. So I'll talk about the simplest case of fluid mechanics, which already is still not understood. And that is the case of a fluid that is incompressible. Incompressible in this context means simply that the speed of the fluid is small compared to the speed of sound. So as you know, the speed of sound is related to the compressibility of the fluid. So if the fluid is moving very slowly, it's equivalent to assuming that it is not compressible. That is that the density is equal to 1. So this actually has many, many applications. Certainly the movement of air in the Earth's atmosphere, the ocean currents, they're all essentially subsonic. So this is, although in terms of theoretical physics, it looks like a tight restriction. It has, in fact, many applications. Yeah, there's a bit of an echo still. I don't know. Yeah. So, so once you set the density to be a constant, conservation of mass becomes the statement that the divergence of the velocity field should be 0. So that is another way of talking about incompressibility. Okay, so the basic idea, because this is classical mechanics, is to go back to Newton's laws and look at the equation that sets the acceleration equal to the force divided by the mass. So we take a small fluid element and we find this acceleration. And you must remember that the acceleration is not just the partial derivative of velocity with respect to time, because the fluid element itself is moving with time. So there are two components to the time derivative, the explicit time derivative and the implicit derivative because of the transport of the velocity along the velocity lines themselves. So the left-hand side is the acceleration, and the right-hand side is the gradient of the pressure. P is actually the pressure divided by density, density being a constant. I can take it inside the derivative. And that is the force. So this is the equation that derived by Euler many, many years ago, back in the 18th century. So this equation of Euler is a partial differential equation, and given initial conditions, we expect it to have solutions. But as everyone probably knows, this is still an unsolved problem in mathematical physics, whether or not this equation has regular solutions. It is still not established, and frankly, I don't even know what to expect. There are times when I think it obviously must have solutions, and it's just a matter of technicalities, and mathematicians are wasting their time trying to prove something obvious. And then there are other days when I think, oh no, this could lead to a singularity. And what a singularity will mean here is that the hydrodynamic approximation is breaking down. It may be that the gradient of velocities grow with time. And if the gradient is too big, you can no longer apply the hydrodynamic approximation. Because ultimately, of course, the movement of a fluid is really the movement of the molecules that make up the fluid. And the approximation of averaging over the molecular motion and taking the continuum limit may not actually, it's not guaranteed to be true for all time. So there is still an unsolved problem there. I won't address that problem, but one hopes that perhaps some of the things that I'm talking about might someday be useful in addressing this. So the first thing is to notice that pressure really is not a dynamical variable. Pressure can be eliminated by taking the curl of both sides and using some fairly straightforward identities. Now, if you take the curl of velocity, you get vorticity. And the equation can be written in terms of vorticity. And this is a standard thing you'll find in all fluid mechanics books, certainly in the 19th century books. Already, this is very well discussed. But instead of writing it the way fluid mechanics people usually write it, I want to write it in a slightly different way. The way it is written in most fluid mechanics books is, I think, not the natural way, not the geometrically natural way. We can use this identity, which is writing the commutative vector fields in terms of curls. Now remember that the velocity field has zero divergence. So these terms are actually zero, which means that the commutator can be written as the curl of the cross product. This commutator is really what appears in the equation. So I want to write the vorticity form of the Euler equation in this way. So this is not original to me. For example, Arnold's papers on fluid mechanics, which are classic in the subject, already he makes this point. But so it is quite natural for a mathematical physicist, but in the usual fluid mechanics books, which are mostly written for engineers, they don't write it this way because I guess they don't really think about commutators of vector fields. So you should really think about the velocity, about the vorticity as the dynamical variable. And that velocity is a derived quantity obtained by solving this differential equation. The fundamental dynamical variable of incompressible fluid mechanics is vorticity. And given boundary conditions, we can always reconstruct the velocity from it. And that is the point of view I will take, that the dynamical variable is vorticity, and velocity is the solution to this differential equation with appropriate boundary conditions. Now, there is a small technical point here, which I will return to, and I'm sure you've already noticed that perhaps, which is that if the underlying manifold is not simply connected, if the first homology is not zero, then there is not a unique correspondence between vorticity and velocity. And then you need to modify this slightly, but that's a minor modification, I believe. What you need is to allow for sort of constant vorticity, which cannot come from any velocity field. And you need to extend the notion of curl a little bit in order to do that. I'll come back to that if I need to do that. So this is a little bit of a technical point, which I'll skip for the moment. Okay, so in any dynamical system, the first thing we ask for are what are the conserved quantities. Oh, by the way, let me stop here and ask for any questions. This is sort of the classical part of the story. Everything I said so far is sort of 18th century physics. It goes back to Euler himself. If there are no questions about this, I will move on to the question of conserved quantities. So what are the conserved quantities? Oh, again, yeah. Because we are talking about a system without dissipation, I haven't allowed for viscosity. That is, I'm talking about Euler equation and not Navier-Stokes equations. So because there is no dissipation, energy is conserved. In fact, ideal fluid mechanics of the kind I'm talking about is a Hamiltonian system. It has Poisson brackets and a Hamiltonian. And that is, in fact, a good way to think about it. So the Hamiltonian is obviously a conserved quantity, total energy. Now, in an ideal fluid, there is no potential energy. All the energy is kinetic. The pressure, the compressibility, of course, is a form of potential energy. If you compress a fluid, it has potential energy. In the absence of compressibility, and in the absence of other external fields like gravity, perhaps, it is all the energy is kinetic. By the way, this already implies something beautiful about ideal fluid mechanics. If you have any mechanical system, all of whose energy is kinetic, then we know from general principles that the equation of motion is describing geodesics, because kinetic energy is quadratic in velocities. It determines ultimately some kind of metric tensor on the underlying configuration space. And if in fact kinetic energy is all of energy, the Hamiltonian equations that follow from kinetic energy alone are going to be the equations of a geodesic. So this is basically an observation of Arnold back in 1960. He showed in much more detail that in fact the ideal equations of an ideal fluid as determined by Euler are really describing geodesics with respect to a metric tensor. And what is the underlying configuration space? The underlying configuration space is the group of diffeomorphisms that preserve volume preserving diffeomorphisms. That's an infinite dimensional Lie group, and there is a metric on it. This metric is, of course, a curved metric. Although the space we live in is Euclidean space, the configuration space of the fluid is an infinite dimensional curved manifold, and the equations of an ideal flow are in fact the geodesics of this. And that Arnold took this quite far. He computed the curvature of this metric and showed that except for a few uninteresting directions, the curvature tensor, more precisely the sectional curvature, is negative, which implies that the fluid is highly unstable. So he has this idea that the instabilities of fluid mechanics, which everybody knows, fluids are highly unstable systems, can be explained by this geometric observation. I won't quite go in that direction, but this is one of my motivations for coming back to this subject. I believe that this insight of Arnold is somehow very important. But today, most of what I'll talk about has to do with another conserved quantity in addition to energy, which is called helicity. This is in fact known for quite a long time. It goes back to, again, the 19th century in the work of people like J.J. Thomson or Lord Rayleigh, people like that. So they noticed that there is another somewhat mysterious conserved quantity in fluid mechanics, which has to do with the integral of the dot product of velocity and vorticity. Now, to prove that it is conserved is quite straightforward. I've given a one-line proof here. And the first part of what I'll talk about is what is really the meaning of this thing of helicity. That's really what I was trying to understand. How should we think about it? So the first thing to notice, which I could describe the calculations a little bit, but really the most important thing to notice is that helicity, of course, is a conserved quantity, so it must commute with the Hamiltonian. It has 0 Poisson bracket with the Hamiltonian. But if you look at the Poisson brackets of vorticity, by the way, the Poisson brackets of vorticity form a Lie algebra, and that Lie algebra is simply the Lie algebra of incompressible vector fields. The set of vector fields whose divergence is equal to 0 is a Lie algebra under the commutator. The commutator of two vector fields is again of 0 divergence. And from that point of view, the vorticity is sort of the momentum map. That is, it is the generator of these infinitesimal diffeomorphisms. And so we know the Poisson brackets. Those Poisson brackets come from the Lie algebra. By the way, more abstractly, the dual of any Lie algebra is a Poisson manifold. So that's what we are using here. So we have the Poisson brackets, and now you can verify that this helicity is not just a conserved quantity. It's something stronger than that. It doesn't just commute with the Hamiltonian. It commutes with any function of vorticity. Every dynamical variable commutes with helicity, not just the Hamiltonian. So it's something much stronger than a conserved quantity. So that is the hint we have. It is something like a Casimir element of it belongs to the center of the Poisson algebra. So to understand this better, I want to talk about a more elementary system. It is also due to Euler. In fact, there are two famous Euler equations in physics. There is the Euler equation of fluids, and there's the Euler equation for a rigid body. And we will see that there is a very close analogy between the rigid body and the ideal fluid. I'm sure that Euler noticed this before there was a concept of a Riemannian metric or a Lie algebra or things like that. I think to see that there is a clear analogy between the rigid body and the ideal fluid is possible to see that there is such a close analogy, and he must have known this. He might have even talked about it, but I am not familiar with the original literature, so I don't know if he actually commented on it or not. But he must surely he knew about it. So let me review a little bit the rigid body mechanics. I'm talking about a rigid body in the absence of external forces, external torques. So in the absence of external torques, the equation of motion for a rigid body says that angular momentum in an inertial reference frame is conserved. But the inertial reference frame is not the convenient frame in which to write the equation for a rigid body, because the rigid body might have a moment of inertia matrix, which is a symmetric positive matrix, and it might have unequal eigenvalues. So if it has unequal eigenvalues, the frame in which that moment of inertia is diagonal is going to be not is not going to be an inertial frame. As the body rotates, the frame in which the moment of inertia is diagonal will rotate with it. So you need to write the equation in a frame which is co-moving with the rigid body. And in that co-moving frame, the total time derivative of velocity, of angular momentum, is the time derivative, the explicit time derivative, plus another term that comes from the rotation of the frame itself. And that's going to be the cross product of velocity and angular momentum. And of course, angular momentum and angular velocity are related by the moment of inertia. G is a symmetric tensor, which is the moment of inertia. So this equation is actually very similar, I will argue, to the equation for a ideal fluid. The analog of angular momentum is vorticity. The analog of angular velocity is the velocity of the fluid. And the analog of the commutator is the cross product. As you know, the cross product is the Lie bracket of the rotation group. It is the simplest non-trivial Lie algebra that appears in physics. So that Lie algebra is somehow underlying the rigid body. And again, in this Arnold point of view, the Euler equations of a rigid body describe geodesics on the underlying Lie group. They describe geodesics on the orthogonal group. The metric tensor of that geodesic motion is given by the moment of inertia. Moment of inertia is not an invariant tensor. Remember that the Lie group SO3 has a metric that is invariant under both the left and the right actions. But it also has metrics which are only invariant under the left action and not the right action. Where, for example, I give some metric tensor on the tangent space of the identity, and then I transport it everywhere by left action, I will get a metric on the Lie algebra which is left invariant but not right invariant. And that is the metric whose geodesics describe the motion of the rigid body. Okay, so what is then the analog of the moment of inertia in the case of fluid mechanics? It is the operator of curl. Curl is actually a symmetric operator on the space of vector fields. And you can see that by integration by parts, the antisymmetric part is a total derivative. So the curl should be thought of as a symmetric tensor on the space of vorticities, on the space of incompressible vector fields. So that plays the role of moment of inertia. So there's a very close analogy between the rigid body and the fluid mechanics. So let me stop here and ask for any questions or comments.
I have a question.
Before I go on.
I have a question.
Yeah, please ask.
You have said that the commutator of two vorticities is again two is again vorticity, is the closest on Lie algebra.
The commutative of two incompressible vector fields is again incompressible. That's right. Yeah.
However, the divergence of omega is 0.
Yeah.
That equation involves a metric.
Yeah.
So there are, but metric is, so the metric is changing from point to point. It is not a flat metric. So
I will only consider a flat metric. So the metric you're talking about is the metric of ambient space, right?
yeah,
I'll choose that to be flat.
you choose it to be flat.
Yeah.
Oh, I see. Okay.
Yeah. Yeah.
All right.
You can modify this to include curve metrics, but the physically interesting case is just flat metric.
But the metric on the diffeomorphisms is not flat.
That's not flat. Yeah, that definitely, yeah. Even if the metric in the Euclidean space is flat, the metric on the group of incompressible diffeomorphisms is not flat.
What is that metric on diffeomorphisms?
It comes from, it's the L2 metric actually, because it comes from kinetic energy.
Oh, I see. But it
So the
looks,
kinetic energy is the integral of v squared. That's the L2 metric of velocity. So
I
if
see.
you take the group of incompressible diffeomorphisms, its tangent space is the space of vector fields with divergence equal to 0, which are basically velocity fields.
Okay.
And the L2 metric on velocities gives a metric on the group. So that metric on the group is left invariant but not right invariant.
Okay.
And that is the metric that, yeah. So I won't directly use that metric today, but it is a very interesting object. I mentioned it because this work of Arnold clarifies that, and that was the thing that got me more interested in this field a second time.
Okay.
Yeah.
So can you say what carries the fundamental representation of the diffeomorphism group?
The analog of the fundamental representation is the space of scalar fields.
Basically
Of scalar.
So it's essentially L2.
Yeah, that's right. Yeah, that's right. The scalar fields because we are talking about incompressible vector fields, they preserve the density on there's a volume form that is preserved. So there's a natural way you can talk about L2 in a product on scalars.
Okay, go ahead, Veseland.
Is this metric, are the geodesics describing only the spatial part of the, what about the non-stationary flow?
I think your sound is very low, Veseland.
What if you have a non-stationary flow? So is this, I mean, these geodesics, it's only the spatial part of the space, right? Time is not included, is it?
That's right. Yeah. So that's right. But the flow need not be stationary. Stationary in fluid mechanics means a flow whose partial time derivative is 0. So that's the particular case where velocity commutes with vorticity. So stationary flows correspond to the case where this by itself is 0. So at least that's what stationary usually means in fluid mechanics.
Okay, non-static then, non-static, whatever.
Okay, yeah, that's right, yeah. So in general, the metric I'm talking about is not the metric of space-time or space, because that is just flat. The metric is the metric on the underlying group of diffeomorphisms. That is what has a, so there is a precedent for this. The rotation group has a metric on it, and that metric is curved even though Euclidean space is flat. So this is something like that, but carried out at a more intricate level.
And one other question, your equations look like covariant derivatives. Can I not promote them with a connect?
There is indeed such a meaning. You can think about the equations or the Euler equations as the statement that a kind of covariant derivative is 0, so that these equations really do describe geodesics. But that covariant derivative is something that lives on the configuration space, which is the diffeomorphism.
But if I think of V here, I mean,
yes,
it looks like it would have an adjoint action on omega.
That's right, yeah. That is in fact one way to interpret this. Okay. In fact, one way to think about this is that omega belongs to the dual of the space of vector fields. The space of velocity fields is the tangent space to the group, and vorticity belongs to the dual. So the map from velocity to vorticity is a metric tensor, is an inner product.
Whereas your equation for the rigid body looks like it would be maybe a fundamental representation, or
it is the sort of the defining representation or the adjoint representation.
The defining representation.
It is the actually, to be really precise, both in the case of the rigid body and in the case of the fluid mechanics, this is the equation lives in the space of it is the co-adjoint representation, strictly speaking, that is happening. But I don't need to distinguish.
Okay, the co-adjoint representation.
Is there a way to the equation in the hydrodynamic equations?
I couldn't quite hear that.
Okay. Is there a way to embed the rigid top equation in the hydrodynamic equation?
Yeah, actually, yes. A particular movement of the fluid is when the entire fluid either rotates or rotates around some axis. So that part of the fluid motion is, of course, a rigid body motion. Because a particular case of a volume preserving diffeomorphism is a rotation. So in fact, the equation for the rigid body is a particular case of the equation for an ideal fluid. But that is usually the uninteresting part of fluid motion, because that's the part we understand. The overall rotation of the fluid around some axis is something we do understand. Are there more questions?
I think you can go ahead for the moment.
Okay.
We will interrupt as we go along.
Please do interrupt me. Okay, so now I want to come back to the question of what this helicity means. So remember that helicity is a conserved quantity in fluid mechanics, but it is more than a conserved quantity. It is a Casimir element of the underlying Lie algebra. It has zero Poisson bracket with every dynamical variable, not just energy. But we have such a thing also in rigid body mechanics. In the case of an ideal, in the case of a rigid body, there is an analogous quantity, and you may remember that the underlying Lie algebra for the rigid body is the Lie algebra of rotations, and the Lie algebra of rotations has L squared as a Casimir element. In fact, L squared commutes with all the components of angular momentum. Therefore, it commutes with any function of angular momentum, not just energy. It commutes with energy, so it is conserved, but it is more than a conserved quantity. It is in fact something that belongs to the center of the Poisson algebra. And so helicity is the analogous quantity in fluid mechanics. So this is an algebraic meaning for helicity. Helicity in fluid mechanics should be thought of as the analog of L squared. Now, the reason why L squared commutes with L, with the angular momentum, is that the dot product in ordinary vector calculus, that dot product is, of course, invariant under rotations. The rotation Lie algebra has an invariant inner product, and L squared is simply a consequence of it. So there must be, therefore, an underlying inner product on the Lie algebra of vector fields, which are incompressible. And that inner product must be the thing that determines helicity. Helicity is the quadratic form associated with that inner product. And if you look a little bit deeper, you will see that indeed there is such an inner product. So I will give a short proof that this is an inner product in the space of incompressible vector fields. So U and W are vector fields that satisfy the condition that the divergence is 0. Now, given a vector field whose divergence is 0, I can find a sort of potential for it. I can find something of which it is a curl. because the divergence is 0, I can find a magnetic vector potential. So I will call that curl inverse. Curl inverse is the solution to the equation that the curl of W is equal to something. So curl inverse is a sensible thing given some boundary conditions. Now, I argue that curl itself is a symmetric operator. So its inverse is a symmetric operator as well, essentially by integration by parts. And now the integral of U dot the inverse of the curl times W, that is a bilinear in the Lie algebra of divergence-free vector fields. And now one can verify that this is, in fact, an invariant inner product. That's a short calculation. The requirement for an invariant inner product is that this quantity should be equal to that, up to a negative sign. This is the condition for a bilinear to be an invariant of the inner product. And that ultimately comes because of the relation between the commutator and the curl. For divergences vector fields, the commutator is the curl of the cross product. So when you take the curl inverse of the commutator, that is just the ordinary cross product. And obviously, the ordinary cross product is antisymmetric. And using that antisymmetry, we can verify that this is indeed an invariant inner product. So the group of rotations has an invariant inner product, and then it also has a non-invariant inner product that depends on the moment of inertia. So there are two inner products on the rotation group. One that is natural, that doesn't depend on any property of the body. That is just a geometric object that comes from the dot product. But it also has another inner product, which is not bi-invariant, which depends on a property of the body, namely the moment of inertia. In the same way, in the case of fluid mechanics, the Lie algebra of volume preserving diffeomorphisms has a natural inner product that does not determine any equation of motion, but it leads to a conserved quantity.
Can I ask a question?
Yeah, please ask.
If I put the fluid in the vessel, okay?
Yes.
I mean, you're assuming boundary conditions that the curl, the vector potential vanishes. You're writing the omega as a curl of some field, and you are assuming vanishing at infinity.
Yeah.
No.
So that's
So
right. So
suppose I take a vessel. So in the vessel, this there are things happening on the boundary of the vessel.
yes.
Then the operator you are getting is only symmetric. It is not obvious that it is essentially self-adjoint. Okay?
Yeah. So there is some. I'm skipping over some issues about boundary conditions. So the boundary conditions for an ideal fluid is that the velocity at the boundary should be tangential. That is the normal component should be 0. That is simply the statement that the fluid doesn't cross the boundary. So with that boundary condition, one can again verify that the statements that I'm saying are true. I'm actually going to finesse that a little bit. The case that I will study in more detail is actually the case where there is no boundary and the underlying space is a torus. Technically, that's a little simpler. But the more physical thing is what you're saying. If there is a boundary, which is the container, that is the correct physical thing to do.
So is it what I mean is, I would expect a priori that to get a self-adjoint operator for this field, there will be some family of self-adjoint extensions.
That's right. Yeah.
So
that's right. So there is a theory of it. People have looked into it. I can't remember off the top of my head exactly how it relates to the to this theory of self-adjoint extensions. But if you impose the boundary condition that the velocity is tangential and that the vorticity is normal to the boundary, then everything goes through. I think that is one particular self-adjoint extension of the operator curve.
This reminds me, but maybe it's of the Atiya Pado, the singer boundary conditions.
Quite possible. Yeah. quite possible. Because it's an odd dimensional manifold, yes, it is very possible, yeah. Because this curl is essentially the exterior derivative and it's adjoint.
There they write it for Dirac operator. My
Yes.
recollection is that it is quite similar to what you're writing.
Yeah. No, Atiyah Patodi also have a theory for exterior derivatives on differential forms.
Indeed, yes.
On odd dimensions. So this theory is a special case of that somehow.
Yes.
Hello, excuse me for a relatively strange question. I logged in exactly at 3 o'clock Dublin time, and you were already in the middle of the. When did you talk? How slide number? What is the slide we are seeing now?
I'm sorry, I'm taking up. I'm sorry, I took up too much time. I haven't. I was going kind of slow. I'm only about halfway through, in fact.
Ah, okay. I'm sorry. No. I will later look. I'm very interested in your talk. I will later look at on the video. Sorry for asking and interrupting you.
Oh, I'm sorry. I probably should have. I should have probably gone a little faster, but I just wanted to answer all.
No. Yeah, Jens has just joined us, and he wasn't able to join earlier, so he's very happy that you haven't gone faster.
Oh, okay,
yeah,
that's good.
Right. It's
that's
the
good,
opposite question.
Okay. In that case, you're good because I'm really barely halfway through. Yeah. Okay, so I want to now point out that helicity is actually a well-known quantity in fluid mechanics. It has been, as I said, known since the 19th century, and it has attracted a great deal of attention in modern fluid mechanics literature. For example, Moffat has a really beautiful paper back in the 60s where he has shown that helicity has a topological meaning. Now, this shouldn't surprise anybody here because I think you've already noticed that helicity looks like the Chern-Simons invariant in an abelian gauge theory. It is the dot product of V and the curl of V integrated. So it clearly has a topological meaning. So what Moffat has shown is that helicity is the average linking number of fluid streamlines. That is, if I take 2 points in the fluid and I follow their streamlines, they describe a pair of curves. And these curves in general are going to be knotted relative to each other. They're going to link each other. So if you take the Gauss linking invariant, which is an integer, and then you average it over the initial points. Of course, the average of an integer is not necessarily an integer anymore, but it is still an invariant. And what Moffat showed is that that invariant is helicity. I'm not going to give any symbol. I don't know of any simple way to see that. It is a fairly deep argument, and both Arnold and Moffat discovered this. And Moffat's paper, I think, is very clearly written. And it really is a classic paper of fluid mechanics. Okay, so I want to summarize what I said so far in this one slide. That there is a close analogy between rigid body mechanics and fluid mechanics. The angular velocity is like the velocity, angular momentum is like vorticity. The inertia, the moment of inertia is related to the curl, is analogous to the curl. The underlying configuration space is the Lie group of SO3, and its Lie algebra is the Lie algebra of vectors in the case of the rotation group. In the case of the fluid, the underlying configuration space is the group of diffeomorphisms, and the infinitesimal version is the Lie algebra of divergence-free vector fields. The Lie product is the cross product for the rigid body, and it's the commutator in the case of the fluid. The invariant inner product in the case of the rigid body is the dot product, and the invariant inner product in the case of fluids is the integral of curl inverse sandwiched between U and W. So this is what becomes helicity. The equations of motion are clearly very similar, with the commutator replacing the cross product. The energy can be written as the dot product of angular velocity and angular momentum in the case of the rigid body. It is half the dot product of angular momentum and angular velocity. Exactly the same way, the energy, which is usually written as the dot product of V with itself integrated, can also be written as the inner product of V and omega, which is the invariant inner product. This angular brackets are the invariant inner product. So it's exactly analogous. The Casimir invariant is just the dot product of angular momentum with itself, the usual L squared. And in the case of the fluid, it is the helicity can be written as the integral of velocity dot product with vorticity, which is the same thing as the inner product of vorticity with itself, with respect to this invariant inner product. The Poisson bracket, which is a Hamiltonian system, so the underlying Poisson bracket has to do with the cross product in the case of the rigid body, and has to do with the commutator in the case of the fluid. And you will recognize that this is basically the Kirillov bracket of the underlying Lie algebra. And the equation of motion follows from the Hamiltonian with that Poisson bracket. So that is the summary of, so far I've basically just reviewed classical fluid mechanics, but from a sort of modern point of view, putting in ideas about Lie algebras and invariant inner products and so on.
I have a question, Rajeev.
Yeah,
Okay.
yeah, please ask.
The question is that you talked in between about linking numbers of Moffat.
Yeah.
So the obvious question that comes is some work which I have also been involved in, that if you in the presence of links, one can ask what is the mapping class group of volume preserving diffuse. And one knows that this is related to mapping class groups of prime manifolds, if you like.
Okay. Oh, I see. Okay.
And that leads, so that leads to issues like what happens if you say take a one knot and take it through the second knot. What happens? Has somebody studied it?
I don't know. But you know, questions like this have been asked in fluid mechanics off and on. For example, Thomson back in the 19th century thought about vortices. In fact, that is where knot theory begins. Knot theory began with his attempt to understand vortices in an ideal fluid, except that he tried to explain the periodic table of elements that way. He thought that the fluid was either, and so on. But the underlying mathematics is quite solid, even if the physics turned out to be not right. And that is the beginning of knot theory. And I think I understand what you're asking, which is a deep question in geometry, which is you take a 3-manifold and you cut out an embedded circle, a knot. And then the complement of the knot is a quite non-trivial deep manifold in 3 dimensions. And what are its topological properties? I think that's very interesting. I know some work of people like Thurston on it. And this more recent work by Perelman, by the person who proved the Poincaré conjecture.
I understand. Okay. Yeah, but there is an old paper. It's an old paper by Goldschmidt, who has given a presentation of the mapping class groups when you have these links present. She has written down the full presentation. It is some infinite group.
This is Josh, is it? Josh Gold?
Sorry?
What was the name? Was that Josh?
Goldschmidt.
Goldschmidt.
She was not a student of Thurston, but somebody who was also in Princeton at that time.
I see.
I don't remember that who it was, but yeah.
You know, I don't know this theory very well. I've heard about it off and on because there's such a big literature on knots and geometry related to it. I don't have much to add to that. But of course, maybe what you're suggesting is that story has something to do with fluid mechanics. I would not be surprised. I would not be surprised if fluid mechanics has deep connections to things like that.
Okay.
Yeah. But I don't know much about it myself.
Okay.
Yeah. I will look into it though. So I want to take this idea that the helicity is an invariant inner product further and really ask, what is it really telling us? What is the meaning of helicity? Now, there's an important difference between the inner product of the rigid body and the inner product in the fluid mechanics, which is that the inner product in the rigid body is positive definite. Now, we understand that because it's a compact Lie group, the invariant inner product is positive. We understand that. Of course, that's not at all true in the case of the fluid. The fluid is a vastly more complicated system, not only because it's infinite dimensional, but because we know that even a finite dimensional approximation to fluid mechanics is chaotic, while of course the rigid body is an integrable system. It is already essentially solved by Euler and Jacobi. So the helicity is, first of all, not positive. That's obvious because helicity changes sign under parity. So it changes sign under parity, so it cannot be positive. Roughly speaking, helicity thought of as an inner product has equal numbers of positive and negative eigenvalues. It has signature plus minus. Of course, on an infinite dimensional space, but there is a sort of symmetry between the positive and the negative signatures. So helicity is an invariant inner product which is of non-compact type. So the proper analog is not the rotation group. A better analog, to have a finite dimensional analog, you should really think about the Lorentz group, or more precisely, SL2C, which is the complexification of the Lie algebra of rotations. That has an inner product. So I'm thinking of SL2C as a real Lie group. It is a real Lie group or a real Lie algebra of dimension 6. So it's basically the Lie algebra of Lorentz transformations. In physics, that's a good physical interpretation. Now that has an inner product, which in the language of 2x2 matrices, it is the imaginary part of the trace of matrices. Now notice that I'm not taking A adjoint B. This is just AB. A adjoint B is not an invariant for SL2C. So this is a positive inner product. By the way, if you want to think of it in terms of familiar Lorentz group, it is actually this invariant, E dot B, in the case of, in the language of Lorentz, in the language more familiar to physicists, it is just the inner product, E dot B, which is of course an invariant of the Lorentz group. So what does this mean? What does it mean to have a Lie algebra with an invariant inner product of this type? This is what I was asking. So it took me a while to place this in the right context. It turns out that I knew the answer all along. It is just that I never expected the connection that turned out to be important, because I heard about it in a completely different context. In the context of Lie bialgebras and quantum groups and Hopf algebras and so on, it was already a well-known thing. Although I'm not a specialist in the subject, I too knew this, but this is the connection I want to emphasize. If you have a Lie algebra, which can be split into two subalgebras, A and B, and if it has an inner product with respect to which A and B are isotropic, then we have something called a Manin triple. A Manin triple is a sort of reformulation of the idea of a Lie bialgebra. The idea of a Lie bialgebra was, I suppose, essentially goes back to the work of Fadeev and collaborators on integrable systems back in the 80s. But the modern reformulation of it is by Drinfeld. And Manin had his own take on what a Lie bialgebra is. And Manin's interpretation is this, that so let me define what a Manin triple is. So for the moment, I'm talking about finite dimensional theories, finite dimensional Lie algebras, although I really need infinite dimensions for the physical application. So this is the definition of a Manin triple. A Lie algebra with an invariant inner product, which has the right signature, equal numbers of positive and negative, can be split into two subalgebras which are isotropic. Isotropic means that the inner product vanishes. If you like, they are null vectors. A and B are null vectors with respect to this. And if that is the case, the two Lie algebras A and B are dual to each other in the sense of the inner product. The inner product is invertible. So if it vanishes in A and if it vanishes in B, it means that A and B are dual to each other. In fact, there will be a basis such that the basis in A is exactly dual to the basis in B. And an example of this is in the case of SL2C. In the case of SL2C, I have two subalgebras. Now, SL2C, remember, is the Lie algebra of 2x2 matrices of zero trace. Of course, a subalgebra of that is SU2, namely the space of anti-Hermitian 2x2 matrices. Now, normally, at least in physics, normally we take a matrix and we split it into anti-Hermitian and Hermitian parts. That is not the right thing to do here, because the anti-Hermitian part is a Lie algebra, but the commutator of Hermitian matrices is no longer Hermitian. So that is not a Lie algebra. That's not what we want. But there is another splitting, which is well known in the theory of Lie algebras. You can split it into a compact subalgebra, which is SU2, the space of antisymmetric matrices, and another one, which is the same dimension, also dimension 3, which are upper triangular matrices. These are upper triangular matrices in SL2C. They must have 0 trace, and not only are they upper triangular, the diagonal entries are real. You can easily count and see that this is a 3-dimensional subalgebra. The commutator of upper triangular matrices is again upper triangular. In fact, it is a solvable Lie algebra. So by splitting SL2C into a compact subalgebra and a solvable subalgebra, we get a Manin triple. And this idea can be extended to even SLN. And in fact, there is a whole literature on Manin triples and so on. Now, why is a Manin triple so interesting? So a Manin triple is really the same thing as a Lie bialgebra. So let me try to clarify that connection. What is a Lie bialgebra, and why is a Manin triple the same thing as a Lie bialgebra? If a Lie algebra has an invariant inner product of that appropriate type and subalgebras, then there is a basis, the basis in A, and there is a basis in B. And because they are separately subalgebras, they must satisfy a commutation relation like this. Then you can prove that the mixed commutator, the commutator of something in A with something in B, must have this form. In other words, the mixed commutators are completely determined by the property of the invariance of the inner product and the commutators in the A and the B. The structure constants in A and the structure constants in B completely determine the mixed commutators. Now, of course, you might ask, what does the Jacobi identity imply for this? The Jacobi identity for gamma and mu are the obvious things. They satisfy the Jacobi identity separately in gamma and mu. The Jacobi identity for the mixed commutator has a very interesting geometric meaning. It means that mu is a element of is closed in the cohomology of A. A is a Lie algebra, remember. So mu is an element, is a closed element in the cohomology of A valued in A tensor A. That may or may not mean something to you, but if you are conversant with Lie cohomology, I had to struggle to understand this, but I think I do finally understand it. So what does that mean? That now can be translated to another algebraic statement. What it is saying is that remember that mu is a map of B tensor B to B, because that's the Lie bracket in B. But B is dual to A. Therefore, mu can be thought of as a map from A to A tensor A, because B is the same thing as the dual of A. A map from B tensor B to B is naturally equivalent to a map from A to A tensor A. So mu is a coproduct on the Lie algebra A. A and B are dual to each other. So if B is a Lie algebra, then A has a coproduct. And this coproduct turns A into a Lie bialgebra. But for that, not only should mu be a co-Lie algebra, which is basically saying that the dual is a Lie algebra, you also need that mu be an algebra homomorphism. That is, mu is a map from A to A tensor A. A is a Lie algebra. So it makes sense to ask whether mu preserves the bracket in A. That compatibility condition is exactly the same thing as the Jacobi identity for this mixed bracket. I think this is a pretty remarkable situation, which was essentially discovered by Manin. So this definition of the Lie bialgebra is due to Drinfeld. And Manin translated that into this other language. And I think that this translation somehow makes me understand what a Lie bialgebra is. So this is really a very nifty piece of mathematics that turned out to be quite useful in what I'm doing. So let me pause here for questions, because these are the two things that I want to tie together: the physics of fluids with the mathematics of Lie bialgebras.
Okay, I am again. Let me ask one more question. Okay?
Yeah, please ask.
There is this construction of Hitchin, where
Yes,
you take Tm and T star m. Okay, so
okay.
That naturally involves a bilinear form, which is similar to the bilinear form you're writing here. So I was wondering, so it is also not just a Lorentzian signature, you can write it down, because you couple the cotangent vector to the tangent vector. So the metric is, I think, 0, 1, 1, 0. Okay. Now the issue I am asking is there such a thing here that one of these algebras can be identified as, say, tangent vectors in some manifold? Okay?
There is. Yeah, of course there is. Maybe it'll become a little clearer soon. There is a group to which A is tangent, because A is a Lie algebra. So there is a Lie group associated to it.
And B? And B also.
Similarly for B. Similarly for B.
So this is the same as the Hitch, looks similar to the Hitchin system.
It might be, yeah, but this is a little more special because both A and B are groups, and in the theory of Lie bialgebras, these groups are in a sense dual to each other.
Okay.
So, for example, the group of rotations is dual to the group of upper triangular 2x2 matrices.
Okay.
That's right. So they are indeed dual to each other. And there's an absolutely amazing, beautiful theory of Lie Poisson groups with this duality playing a deep role. It is a generalization of the theory of coadjoint orbits. The usual theory of coadjoint orbits is a particular case where B is abelian and A is the rotation group, for example. The deep thing is that there is a generalization of all that to the case where the dual is a non-abelian Lie group. And it fits amazingly well. I mean, there is a whole theory, dressing actions and so on. I mean, by now there are probably literally hundreds or maybe even thousands of papers on it. There are thick books. And I highly recommend the book by Chari and Presley, which is where I learned most of this from. It is a book from the 90s. And it is a good, solid introduction. Although the theory has evolved further. But in fact, all the mathematics that I'm using now is at least 30 years old. It goes back to the 90s. So yeah, so there is such a theory. Now I think that maybe there is something more to be learned by sort of extracting more information out of all that math. So why is a Lie bialgebra interesting? So that is the next topic I want to talk about. What is the meaning of a Lie bialgebra? So I think that where I'm headed, I think you can see what I'm trying to say is that classical fluid mechanics, good old 19th century or 18th century classical fluid mechanics has the property that the underlying symmetry group, the underlying group of Lie algebras is not only a Lie algebra, but is a Lie bialgebra. That is the meaning of Helicity. The meaning of Helicity is that the underlying group of rotations, differmorphisms, has the structure of a Lie bialgebra. But what is a Lie bialgebra? It is an absolutely beautiful and deep thing in mathematical physics. And the most important property of it is that a Lie bialgebra is the infinitesimal form of what is colloquially called a quantum group. A more precise statement is that a quantum group is a colloquial name for an object which is a Hopf algebra. A Hopf algebra is an associative algebra on which there is also a co-multiplication defined, and there are certain rather tight constraints that tie together the multiplication and the co-multiplication. I won't list them here. There's a pretty standard literature on it. An example of a Hopf algebra is the universal envelope of a Lie algebra. That happens to be a co-commutative but not commutative Hopf algebra. And yeah. Excuse me.
But you need an antipode as well.
That's right. That's right. That's important. Yeah, exactly. You need an. I should have listed that here. You also need an antipode. Yes. So you need a. You need a. You need a product.
What is the antipode in the?
Yeah. So the antipode. So the point is that if you have a Lie bialgebra, it should be thought of as the infinitesimal form of a group. So in other words, this was essentially conjectured by Drinfeld, that every Lie bialgebra is the infinitesimal form of a quantum group, of a Hopf algebra, and the antipode will be constructed from the essentially it is the reflection in the Lie algebra that becomes the inverse. It's like x goes to minus x corresponds to g goes to g inverse. So by now, this conjecture of Drinfeld is essentially established in finite dimensions. Indeed, every finite dimensional Lie bialgebra can be sort of exponentiated into a Hopf algebra. I frankly don't understand this theory. I understand particular cases. For example, the case of the matrix groups. But there is a very general theory that is absolutely formidable to me. By Tingoff and Kashdan. They have these 5 massive papers where they have essentially carried through some kind of construction. All I can say about it is that it looks to me like a very far-reaching generalization of the Baker-Campbell-Hausdorff formula, where the infinitesimal Lie bracket allows you to construct a group out of it. So they have found something like that, but for a Lie bialgebra. I cannot explain the general theory, but I understand particular cases. So the particular cases, many of them were discovered by Drinfeld. Many others were discovered by the Japanese group, Ivo, Jimbo, and so on. And they form the basis of the theory. So what I know is what was known in the 90s by Chari and Presley. That is given in the book by Chari and Presley. So let me stop and summarize what I'm saying so far. We have the Lie algebra of incompressible vector fields. It has an invariant inner product which has the right signature. So as long as I can find appropriate subalgebras which are isotropic, I will have a Manin triple. And once I have a Manin triple, I should expect that there is a Lie bialgebra. And that's as far as I've got. To construct the corresponding quantum group is still an open problem. I have not able to do that yet. In fact, I think that's a pretty serious mathematical problem, and some aspects of it I'm working on with our friend Gianni Landi, who's here. Okay, so if there are no other questions, I will now proceed to the next step, which is, I've taken up a lot of your time. Is that okay? I continue?
Absolutely, we've been asking lots of questions. Which
I love the questions. They're very informative for me. Yes. Okay, so remember that I haven't quite constructed a Manin triple yet. So all I have so far is an invariant inner product. I need more. To really construct a Manin triple, I need 2 subalgebras which are sort of complementary to each other, which are dual to each other. So here there is a problem. There is the obvious ways of doing this. These things will not work. So for example, if you take the Lie algebra of the Lorentz group, it has a subalgebra which are rotations. So what is complementary to rotations? Now, physicists normally will talk about boosts, but boosts are sort of conjugate, or they are complementary indeed to rotations, but they don't form a subalgebra. The commutator of 2 boosts is not another boost. But there is a way to split the Lorentz Lie algebra into rotations and these matrices which are upper triangular, which physically can be translated. And it turns out that they are some sort of null transformations. They correspond to, just as the rotation group is the stability group of a time-like vector, this other group B, in the case of the Lorentz group, is the stability group of a null vector. The stability group of a null vector, the little group of a null vector, is an upper triangular matrix. So you can, in fact, find a good analog. And this analog is what I had in mind in order to construct an appropriate pair of algebras in the case of fluid mechanics. So in fluid mechanics, if you look in the fluid mechanics books, they always talk about various sort of subalgebras of vector fields. They may not use the word subalgebra, but that's what they mean. But none of them really are complementary in the sense that I am talking about. So I had to sort of invent something new here. And I'm going to use a trick that comes from the theory of dynamical systems. In fact, this trick I'm about to use appears in Arnold's proof of the KAM theorem. This is where this idea comes from. So now I'm in 3 dimensions. In 3 dimensions, if you consider vector fields that have divergence 0, they have 2 independent components. That is, there are 2 scalars, which you may think of as the scalar components, scalar fields that somehow produce the underlying vector u. So one way to think about it is that if you take the gradient of a scalar field and you take its cross product with a constant vector, you can check that this has zero divergence. Because this alpha, when you take the divergence of a cross product, you can write that in terms of the curl of each of these vectors. And the curl of a constant is 0 and the curl of a gradient is 0. So in the same way, so I asked myself the question, is it possible to take an arbitrary vector field and decompose it this way as the cross product of the gradient of the scalar A with some vector alpha and the cross product of some other scalar B with another vector B. So alpha and beta are constants. This is not the usual decomposition that you find in typical fluid mechanics books.
Is it Klebsch decomposition? Is it Klebsch decomposition?
It is not really the Klebsch decomposition. The Klebsch decomposition is something else. The Klebsch decomposition is something like this.
Yes. Okay.
Okay. So you have 2 independent scalars, phi and psi. So I tried the Klebsch decomposition first. It didn't really, I couldn't construct any least subalgebras out of it.
Okay.
So it is a different decomposition. Of course, each term here has some analogy to a Klebsch decomposition, but the dynamical degrees of freedom are in these 2 scalars, A and B. So alpha and beta are fixed vectors, and A and B are scalars. So I want to impose some periodic boundary conditions. So I'm working on a torus. And so the question is it really true that every vector field can be uniquely decomposed in this way? Of course, unique up to adding constants to A and B. That's what I mean by unique. So with a little trick using irrational numbers, if I choose alpha and beta to be a set of, to be a pair of vector fields with irrational components. Now, irrational components means that the orbit generated by that vector field is dense in the torus. Now, why is that important? That means that there is no scalar that is constant along those scalars, which means that this operator alpha cross gradient is in some sense invertible. If that is invertible, then you will be able to decompose any vector field of 0 divergence into this form. So this is, I think, a non-trivial idea. It is at least not the kind of decomposition that you normally would do in fluid mechanics. It's, I think, a new decomposition of an incompressible vector field into a pair of scalar fields. I have some ideas on how to generalize this to other manifolds than torus, but today I will only talk about the torus. So for example, I may choose this pair of vector fields. So these are indeed irrational, and therefore there are no integers, so that no linear combination of these components with integer coefficients can be 0. And gamma, by the way, is the cross product of alpha and beta. Gamma is going to play a role soon in the story. So now, if I take the functions, the exponential functions, this is the basis for periodic functions on the torus. So this suggests that here is a basis for the Lie algebra of incompressible vector fields. Now you can check that these form a subalgebra and these form a subalgebra, and moreover that that is in fact isotropic. That is, the inner product of two such things is 0. The inner product of two such things is 0, but the inner product of A with B is not 0. So those are the conditions you want to construct a Manin triple. So this is not something that you would do unless you knew about Manin triples. Because I'm trying to construct a Manin triple, I construct this. But this has a nice geometric meaning, by the way. The geometric meaning is actually rather interesting by itself. Well, in an odd dimensional manifold, we don't usually have something like a symplectic form. Because it's odd dimensional, you cannot do that. But in a way, that is what this is. For example, it is as though alpha is defining something like a symplectic form in an odd dimensional manifold. Now you may wonder, how is that possible? How can that be invertible? The point is that locally it's not invertible, but globally it is. And now Gianni tells me that ideas of this kind already appear in some work of Weinstein. I didn't know about it. I've read a lot of papers of Weinstein, but I didn't know about this one. So if you, even in an odd dimensional manifold, you can construct things analogous to symplectic forms, which are in fact invertible, provided that you take advantage of some global property of the manifold. And that's what I'm doing here. But in fact, what I have here are two separate symplectic forms, one associated to alpha and one associated to beta. And the brackets of A with itself is closed, form a Lie algebra. The Poisson bracket within B is closed and forms another Lie algebra. And essentially, the two together gives you the Lie algebra of all vector fields. So now there is a, yeah. Sorry.
What is it? Both alpha and beta have coefficients in irrational numbers. Am I right?
That's correct. Yeah.
So what is the difference between A and B?
So A and B are vector fields that essentially preserve alpha or preserve beta. So yeah, alpha and beta define two independent sort of orbits.
Alpha and beta are fixed.
Alpha and beta are fixed.
Okay, fine. I understand.
Yeah. So this basis depends on the choice of alpha and beta.
Okay. So there are infinitely many such decompositions.
That's right. But I think that I can't prove this, but I believe that as long as alpha and beta are irrational, I think they are all somehow equivalent, and that this is just a choice of basis.
Okay.
Abstractly, they are isomorphic Lie algebras.
Okay.
Okay. So now it is a matter of straightforward but tedious calculation to verify indeed that the commutator of A's is closed among the A's. The commutator of B's is closed among B's. Actually, that is pretty straightforward. Yeah, the tedious part is to verify the mixed commutators. The commutator of A with B is a linear combination of something involving A and something involving B. And the coefficients are exactly what you want. So the coefficients are determined by the invariance of the inner product. So that is the important thing. The inner product of A with B is this. I hope you can see this. Maybe I need to emphasize that. The inner product with A with B involves gamma, and gamma is alpha cross beta. So alpha, beta, gamma, they're all vectors with irrational coefficients. And the inner product of A with B involves gamma. And that, by the way, gamma being irrational also, gamma dot n is never 0, except when n is 0. There are no integers, linear combinations of gamma that are non-zero. That is what makes it an invariant an inner product. That's what makes it invertible. So now the invariance of the inner product guarantees that there is such a decomposition, but we can actually directly verify this. That is the part that is tedious. Of course, I'm very bad at calculations, so it took me a long time to verify this. And in the end, I did it using Mathematica, using a symbolic computational program. It is just a long series of algebraic calculations. So I can now establish that there is indeed a Lie bialgebra. Now there is a somewhat technical digression here, which I might skip in the interest of time, which is that because the underlying space is multiply connected, it is not quite true that the curl is invertible. And there is a little sort of an interesting technical point, which is that there are additional degrees of freedom on a multiply connected space, which are beyond what I discussed. And you can extend the Lie algebra by, you can find a central extension of the algebra I mentioned last time in the previous slide. And this central extension describes the complete degree of freedom for a particle on this. This central extension, again, is not discovered by me. After the fact, I realized that it was discovered in a completely different context by Floratos and Iliopoulos, and they were studying membrane theories. So these are people who study membrane theories. You might remember membrane theories were fashionable in the 90s, and they discovered it in that context, which I can adapt for this purpose. By the way, this entire story has a much simpler analog in 2 dimensions. The theory is completely simplified, totally simplified, but it was already discovered by fluid mechanics people. And I won't go into it, but I give a reference here. Okay, so that is the bulk of the talk, and the rest is basically what I hope to do with these things in the future. So my main message is that the Lie algebra underlying incompressible fluids is actually a Lie bialgebra. And we know from Drinfeld's work that Lie bialgebras are infinitesimal versions of quantum groups. So there is some mysterious quantum group that is underlying the fluid mechanics. That is the group of diffeomorphisms, volume preserving diffeomorphisms, somehow has some sort of a natural extension to a quantum group. And that quantum group should play an interesting role in understanding fluid mechanics. And it all comes because of helicity and because of this invariant inner product induced by helicity. And I think to this audience, it should be clear that I have an ulterior motive in studying such things. My ulterior motive isn't just to understand fluid mechanics, because the same group with some small modifications also appear in relativity. I'm hoping that studying fluid mechanics will also teach us something about quantum gravity. But this ulterior motive, I don't have to mention explicitly. That is sort of underlying the motivation for pursuing this. So let me stop here, and then I will make some comments at the end about what I hope to do in the future.
Okay.
Can I ask a question?
Thank you very much.
Yeah.
Go ahead.
You mentioned, other connections to Virasoro.
Oh, yes.
And possible central extensions. Well,
yes.
I presume you mean this is some kind of higher dimensional analog of Virasoro.
Exactly. That's
yeah.
It. I believe that this is the three-dimensional analog.
Yeah. So with the ordinary Virasoro, one's dealing with S1 and the vector fields on S1.
Yes.
And then one's very familiar with all the physical and mathematical properties of the central extension.
That's right.
But then the representation theory is such that if you didn't centrally extend it, you wouldn't get anything non-trivial.
That's right.
However, I doubt if that still would be true in this higher dimension context. So even if you didn't centrally extend things, you still might get something highly non-trivial.
Yeah, very possible.
Do you have any comments on that?
Yeah, I have some ideas, but not anything I can prove. Okay.
Also, is there a natural reason? See, there's a natural reason for centrally extending things in the S1 case, because it came out of the physics before one even understood what the Virasoro algebra was.
That's right.
The physics determined the irreducibility or the non-triviality. But here, there may not be a motive. Maybe centrally extending is not the great thing that it is in the lower dimension.
So the motivation here is something else, which is fluid mechanics itself. Remember that I said in the beginning that the vorticity is the underlying dynamical variable.
Yeah.
And then that I can sort of invert the equation and get velocity.
Mm-hmm.
That is not quite true in a multiply connected space.
Sure, yeah.
And that is where the central extension appears. The central extension is exactly the extra information you need in order to push that through. So what this essentially does is to extend the notion of curl so that you have a larger space of velocities.
Yeah, I understand the direction you're going in, but how can I see that such an extension, because I believe that would be an extension, is going to be central rather than non-central?
But because you can actually calculate the Poisson brackets and see that it is.
Okay, right.
Yeah.
Because in these high dimensional quantum group type situations or infinite dimensional group situations, there are quite a lot of non-central extensions which are also of interest. They're not just curiosity.
That's correct. Yeah. So here, this extension really is central because that is what gives the right equation of motion.
Okay. Right.
So that's one of the things that I've included in this paper.
Right.
That you can. So this is a sort of clarification of conventional fluid mechanics. There's an enormous literature in fluid mechanics on formulating it in terms of vorticity.
Mm-hmm.
But multiply connected spaces are usually not interesting to fluid mechanics people because they are sort of engineers. But this little story about central extensions fits nicely with that story.
Yeah. On a slightly informal note, I don't know whether the fluid dynamics community would like you always talking about them as being engineers.
Yeah, I know. I'm sorry about this. Yeah, there are at least 3 groups of people that I know who do fluid mechanics, and they would each find it insulting to be compared to the other 2.
I mean, Moffat wasn't an engineer.
Exactly, that's right. So there are physicists who work on such things, such as Moffat.
Yeah.
There are engineers, and then of course there are mathematicians. There are analysts who prove theorems and so on.
Yeah.
And these are slightly overlapping and perhaps competing communities. Who do fluid mechanics. I didn't mean to use engineer as a pejorative. I'm very much an admirer of engineers, especially fluid mechanics engineers.
Right. Okay. That's really fascinating. I was wondering when you generalize to other manifolds, I could imagine how you do it for hyperbolic ones, but would it even work for spherical manifolds if instead of a torus you just take the sphere? How would you do that?
So I haven't worked it out in detail, but I believe that it will be. I believe that it will be possible. So let me tell you roughly what I'm thinking. Instead of using these irrational constant vector fields alpha and beta, what you need are functions alpha and beta, and then take some sort of gradient of them. So I can do some things even in the case of S3 and therefore elliptic manifolds. But it is not something I've worked out in detail. By the way, the case I think that is of most interest in fluid mechanics is when the underlying manifold is a sphere cross an interval, because that can model the atmosphere.
Let me ask you a quick question. Sorry. Then Domenico.
No, go, please.
I have to leave in 2 or 3 minutes, so I just ask. You have a half algebra. So is it quasi triangular or what?
Yeah. Okay. So let me clarify that. I can prove that it is not quasi triangular. So
yeah.
Okay.
It is not quasi triangular at all. So there is no.
There is. Yeah. This is why I have trouble constructing it explicitly. Okay. So the reason it's not quasi triangular is that this coproduct mu, it is an element of a cohomology, but for quasi triangular Lie algebras, it is known to be an exact element of the cohomology, and I can prove this is not exact. It is close, but it's not exact.
Okay.
So there is no Young-Baxter equation then, right?
That's right. There is no.
Yeah, that was my question. Also.
That's right. There is no classical Young-Baxter. Yeah.
Okay, Rajeev, I have to leave. I have another meeting, but it was a brilliant talk. Second time I'm here, I'm glad I heard it. Okay.
It's always nice. It's like having your mother compliment you. It's always nice to have your advisor in the audience.
Okay. I have to leave now. Yeah.
Okay. Thanks, Val.
Okay.
Thanks, Val.
More questions?
Yeah.
Yeah. So
may I ask one?
Yeah, please ask.
Rajeev,
yes, of course.
What would be the dual fields that you have in mind? I mean, what would be the physical meaning of the dual quantities.
Yeah.
Here
So-
in the hydrodynamics setting, but also in the general relativity case that you mentioned.
Okay, so so in the hydrodynamic setting, these are two kinds of vector fields. They wind around the torus sort of in complementary directions. You know, one set of flows goes around in one way, and the others go around in the opposite way. I probably should have shown a picture of this. I plotted these things so that I have a picture in my head. Maybe I will at some point actually publish those pictures. So you can construct examples of A and B, and you can find their integral curves, and they're basically flows that go around in opposite directions. I don't know. I don't know anything more direct than that as an answer to your question.
Okay.
Now, so this concept of dual groups is quite deep, and I think even leaving fluid mechanics aside, and just going back to classical mechanics, it is, I think, a very interesting and deep thing to study. The mathematicians have developed a very deep and sophisticated theory with many examples. But so far, the physics applications are not as sophisticated. You know, the story started in physics, of course, for Dave and so on. But it has been taken over by mathematicians who have done absolutely amazing work. And I think a lot of this has applications to physics. I mean, not just fluid mechanics. I think it has applications to things like quantum mechanics and things like that. I mean, I have some ideas about those things, but that is in another direction. Yeah.
I have a question.
Yeah.
Very little is known about representations of volume-preserving diffeomorphisms.
Yes.
Have you thought about representations in particular with regard to your splitting and writing it as a Lie algebra? Does it help you to get any kind of non-trivial representations?
I can't. I don't have an example. I don't have a worked out theory, but I believe that it is quite useful to construct such representations. In fact, in some ways, a quantum group is something more general even than a representation of a Lie algebra. Because usually the idea for representation is that you have a commutation relation, and then you find operators in some vector space or Hilbert space that exactly reproduce those commutators. A quantum group is something that allows for certain deformations of these commutation relations, of course, satisfying the axioms of a Hopf algebra. And so in the co-commutative case, it reduces to the conventional representation theory. So one point of view about this theory of quantum groups is that it is a kind of generalization of the usual theory of representations of Poisson or Lie algebras. And this point of view is very much emphasized by Drinfeld. And I believe that this is the beginning of such a theory. And this, remember, I said I have an ulterior motive in studying this subject. And that is the ulterior motive, that I believe if we can understand representations, even of volume preserving diffeomorphisms or the corresponding quantum group, I think that those things are very useful someday to understand quantum gravity. But that is an unspoken underlying motivation for all this. Well, I guess I just talked about it. So it's not
it's spoken now.
Yeah, it's spoken now. That's right.
We'll give you the credit.
It is something that I didn't really want to admit to it because I don't really have a theory. But that is, now that we are talking about speculations, I can talk about it. Yeah.
You've taken the first step.
It is only a first step. That's exactly right. Yeah. That's exactly right.
Can I ask how much of this do you think would go through if you've taken here the torus, the tree torus, if I understood correctly?
That's correct. Yeah, tree torus.
Now, supposing I make it the non-commutative torus or the irrational rotation algebra.
Yeah. This is, of course, that is a very interesting question.
It looks like most of it will go through.
Yeah, so this is related to the sort of things I'm working on with Gianni, in fact. I don't know if he wants to comment on this, but there are some really amazing connections to non-commutative geometry, which we are only starting to work out. So it turns out that this story is interesting even for the two-dimensional torus. In fact, we have gone the other way. We have gone down to 2 dimensions, and we are trying to construct a Lie. We found some interesting Lie bialgebras in the non-commutative tutors. So Gianni, should I say more about this now, or?
I don't know. Like you're great. Good.
Yeah, this is work we are still doing, and so somehow when I started on this, I assumed that the two-dimensional that the non-commutative torus in 2 dimensions was so completely understood that such questions would not be new. But Gianni assures me that it is not new. That in fact, the Lie bialgebra is a surprise in that case.
Dentro, the rational case is really a representation of SL.
Yeah, exactly. Well, that's why I was thinking of that.
And that one we've done. We have found a basis, an explicit basis that is really a Manning triple for this rational torus. We've done it explicitly. And out of that, Rajeev came up with a very nice way to break the functions on the ordinary two torus, for which we are still computing the Lie bialgebra structure. So it's quite involved. I mean, you cannot go directly via the Manning. If that one works, and it seems it works, because we are just computing all the single commutation relations. Yeah. As a vector space, this can be used as a basis for the non-commutative torus. And so it will be just a Lie bialgebra structure for the non-commutative torus, the rational non-commutative torus. So it's quite promising. We are on the way. I mean, did I say it correctly, Rajeev?
Yeah, I agree. I mean, that's right. Yeah, I was stuck on all those issues, and then Gianni, of course, is an expert, and they've been able to make a lot of progress together.
Maybe I can actually say why I got interested. I missed this talk by Rajeev in Bal's seminar, and then they had this drive, and then there was a Rajeev paper there. There were no details at all. So there were all these, so I could not understand any single thing that he was doing. And so I started to study the paper, and then I wrote to him, and then we started. So, and I seen all this proof, I would have not written to him probably.
Oh, so the lesson is that I should not explain too much.
Yeah. Okay. But it's beautiful stuff. It is beautiful stuff. Very elegant stuff, and it's a magnificent piece of work, I think. I mean,
thank you very much. Yeah, I know. When I started in physics,
have you thought about extending it to maybe the S2 cross, or just the two sphere, and maybe S2 cross the interval?
Yes. So that I think is the case of most physical interest, because, for example, the atmosphere or the ocean can be modeled that way.
But again, you could there's a non-commutative deformation going to.
So I'm not able to do everything in that case.
Matrix models.
But I have the beginnings of a theory, but not the entire thing. No, not all of this has been. I'm not able to extend the entire thing. But obviously there's an invariant inner product. I can construct these dual algebras A and B, but I cannot directly verify that they are a Manning triple, because these commutation relations are quite formidable in that case. Where the basis involves spherical harmonics and so on, so it's a bit more. But the calculations are formidable. Yeah, but I believe the conceptual framework does extend, and that I'm very interested in this. Yeah.
I'm interested in the representation of the two-dimensional case for the volume-preserving diffeomorphisms. And, my question is, have you thought, I mean, they appear in your case as the subalgebras, like the M cross N with a dotted into alpha or something like that. Okay. Have you thought about representations of the two-dimensional case? I mean, it's,
Yeah, so I did think about it. In fact, I worked out the two-dimensional case first, and then discovered that it had all been done long ago by a fluid mechanics expert, McLaughlin, and it is very much a part of active literature in the numerical solution of differential equations, of Euler's equations. Now, first of all, there is no Lie bialgebra in 2 dimensions. The two-dimensional case is quite different, because there is nothing like Helicity. So there is no Lie bialgebra. There is just a Lie algebra. But that Lie algebra is a very familiar thing to physicists. The incompressible vector fields in 2 dimensions are the same as canonical transformations, because after all, the volume form is a symblectic form in 2 dimensions. The area form is a symblectic form. And
McLaughlin constructed representations?
No, not representations. Because I'll tell you, we all know the analog of representations. So let me explain exactly how that comes about. The classical theory is so incompressible vector fields are infinitesimal canonical transformations. Now, the problem that McLaughlin showed is solved is to find a finite dimensional, in our language, it is a finite dimensional regularization. That is there a finite dimensional Lie algebra, a family of finite dimensional Lie algebras, which in the limit becomes the Lie algebra of canonical transformations? And we know that. That is what we call quantization in physics. Because the Lie algebra of the group UN in the limit as n goes to infinity is the Lie algebra of infinitesimal canonical transformations. I mean, we know this
that part I know. I'm the one who showed that first. But
exactly.
It doesn't help you. Does it help you to get representations of the infinite dimensional algebra?
That's right. So in the
that's the question.
Yeah. Okay. So I don't know the answer to that question about representations. What McLaughlin showed is that this finite dimensional regularization, which is not representations, but it's just another Lie algebra, as you know. It is the sign algebra, as you discovered. It is the thing that allows you to solve fluid mechanics in a very elegant way numerically. So this is very much a part of numerical theory. Now, about representations, I thought of all people, you should be the one to answer that question, because I don't know the answer to that. I don't know what we can say about representations in the sign algebra.
Maybe we had sign algebra is easier. There are representations, but the difficult case is the Poisson algebra, the M cross N case. That is the one where it's difficult to construct representations.
I see.
Yeah.
Because it is infinite dimensional, or is there more to that?
Oh, I don't know. I mean, I actually recently looked again quite a lot into it. I mean, there's lots of progress. The classifying co-adjoint orbits by Rabe graphs, and very interesting, relatively recent progress.
I see.
But if you just ask a simple question, what do you know any other than the natural representation of functions on a 2 torus, Poisson algebra of functions on a 2 torus or 2 sphere? Do you have non-trivial representations? And the answer seems to be people don't know. I mean,
it is pretty amazing that even the case of the Poisson algebra on a commutator torus still is so mysterious. Yeah, I find that amazing.
Thank you very much for interesting talk.
Yeah, thank you. Yeah. In fact, when in doing all of this work you did on this sign algebra, that was very much a motivation. I didn't talk about that part of it, but that was sort of underlying the motivations. In fact, this fluid mechanics book I wrote, I tried to describe some of that, the 2-dimensional theory. Other questions?
Other questions? Well, if not, I can stop the recording and we can go to a less formal format.
Yeah.
Okay.
I'm happy to.
Well, thank you very much again for a fascinating review and insight into this subject.
Thanks for the opportunity.